Algebras. Welcome to your Chapter 12 Lesson 2 notes. We're going to look at graphing exponential functions today. So we've already kind of talked a little bit more about exponential functions as a general piece of all four functions that we've looked at. What I'm going to do today is I'm just going to go a little bit more in depth as to how the equation of the exponential function actually does kind of drive the look of the function as we graph it. Okay, so we're going to start with our very basic exponential function, which is y equals 2 to the x power. And that's what we've looked at in the past, and that's what I looked at in the last video when we were kind of looking at this. But now we're going to look at, okay, here's our initial amount. Here's our base. Our x is our variable that changes throughout, and then our matching y is what goes with it. And then, of course, here is where our asymptote is compared to the rest of the graph. And remember that that asymptote is that invisible horizontal line that you're kind of going towards but cannot touch or cross. All right. So let's start with this basic exponential function again. And again, I'm going to go to my graphing calculator. I'm just going to make it a little bigger for the time being. I'm going to press y equals, and here's where I'm going to type in my function. So it's f of x, or y, equals 2 to the x power. So 2 is my base. And when I want to raise to the x power, I press this caret right here. If you have an older calculator, you won't have this area. You'll have an actual physical caret that will show up. But we have this area where we're going to type the x, and notice it's smaller and up to the right as in our exponent. Okay, so we're putting that x in our exponent. If you press graph, you see it on the graph. And because I have a color graphing calculator right now, you can actually see that this is the asymptote. It looks like my function is right on the x-axis, but we know from analyzation in the past that it's not. It just looks like it because this is as close as our pixels can get without actually touching or crossing, right? So second end graph gives us our table of points. We're going to look from -3 up to, well, what we can fit is +4, 16. But if you kind of look at this and head backwards, let's look past -3. Let's go into the deep negatives. You look at how much smaller and smaller and smaller my decimal is getting, okay? So look at that. See how much smaller that decimal value is getting. It's trying to get closer and closer and closer to 0. If I actually arrow over and look at this, this is the decimal place back -8, right? So 8 places behind the decimal is really where that is. That's really close to 0, but it's still not quite there. And it's never going to actually get to 0, okay? It might, your decimal values might be so small that of course they would round to be 0, but you're never technically at 0, touching or crossing that x-axis, okay? So that's what we want to be sure we're representing correctly when we're putting these points on our graph, okay? So when I go to write this table and put these points on this graph right here, okay, when I go to do this, let me just go from -4 to, what the heck just happened? I apparently can't draw a straight line. Try that again. Okay, so let's just get these points on here from -4 all the way to +6, even though I likely will not be able to actually fit those. Okay, but I want to see the movement that's occurring when x is my exponent, okay, and what's going on with my y's. So 0.0625 is my matching y for -4, and I'll turn that into a fraction so you can see it in a minute. And then, of course, 0.125, 0.25, I'm just scooching this off to the side so it's not right on it anymore. 0.5, and then 1, 0, 1. That's my y-intercept. And then 1, 2, and 2, 4, and 3, 8, and 4, 16. Now look at that. Look at that movement. Then 5, 32, then 6, 64. Now, this grid isn't going to fit a 532 or a 664, but it is going to fit these other integer points. So that's where I start my graph, and then it'll be easier to do those fractional points. And I will convert those into fractions for you in a second. So 0, 1, that's your y-intercept. 1, 2, 2, 4, 3, 8, 4, 16. Okay, and obviously 532 wouldn't be able to fit, but it would be way up here, back where your name is. Okay, be way up there. And now let's zoom way in to go back the other direction and get those fractional points. Okay, so let's kind of think about those. So you've got negative 1.5. So that's 1/2, right? And 1/2 is halfway between 1 and 0. So right there. Okay. Negative 2 is your x value. 0.25, well, that's 1/4, right? So that's going to be like halfway between 1/2 and 0. And then negative 3 all the way up to 0.125, well, that's 1/8. So that's going to be halfway between 1/4 and 0. So see what I'm doing here? I am getting closer to 0. I'm not really going to be able to fit a 1/16. So I'm going to connect what I can right here and put my arrow straight across. So my arrow is not trying to arrow down below the x-axis. That's very bad. There is an asymptote right here that I cannot touch or cross. So I know I'm going to kind of go straight across that. Again, not technically touching it, but I'm getting so close to it, so infinitesimally close. That's the reason that I really can't show any more points fitting there. Okay. So let's zoom out a little so I can connect the rest of the graph. And notice what's happening as y, as your x is increasing, your y is rapidly increasing. Look at this rapid curve increase. Put your arrow right at this point and then label y equals 2 to the x power. Now, on every exponential graph, there is an asymptote that needs to be labeled. So here is my asymptote, y equals 0. ASY, y equals 0. It's a horizontal line, an invisible barrier you cannot touch or cross. Okay, that's what's there. This is an increase, right? So this is as x increases, so does y. So this is what we consider an exponential growth function. And it's rapid growth. See how quickly those y values change? Think about what the base is. What are the y values doing? They're doubling. This is 1/16 as a fraction. This is 1/8 as a fraction. This is 1/4 as a fraction. This is 1/2 as a fraction. Then, of course, 1/2 plus 1/2 is 1. 1 plus 1 is 2. 2 plus 2 is 4. 4 plus 4 is 8. Doubling. That's how I'm getting from one y to the next as I go. Which also means if I'm heading that other direction, this direction, I can also always take half. There's always still another half to take, and another half to take, and another half to take. And it feels like I'm getting close to 0, but I just never get there. On the opposite end of that would be if you have y equals 1/2 raised to the x power. And I say this is the opposite end of that as far as our base goes, okay? So when it comes to our base being a fraction between 0 and 1, this is going to give us the decrease as we go, okay? Because negative exponents flip the base upside down. So this is where we actually kind of start having those big numbers, and then we're really bringing that decrease out. So let me show you how to plug that into your graphing calculator first. Pull this guy out. Y equals, and then here I'm just going to clear this guy out because I'm done. And I'll put front parenthesis 1 divided by 2, end parenthesis. Now I use my caret button to put my x just like I did before. This is saying that that 1/2 is my base and all of it's being raised to the x power. So if I press graph, I'm going to see it. And just like I mentioned, it's going that opposite direction curve-wise. As y increases, or excuse me, as x increases, because we go left to right, as x increases, y decreases this time. This is what we call an exponential decay. Okay, this is exponential decay. Press second and graph to see your table of points and look at that. Look at how it goes this time. We start higher and go into the lower, into the fractions as our x increases. So as x is getting bigger, y is getting significantly smaller. In fact, it's cutting in half, okay? So it's that opposite direction of that. So what I'm going to do this time is I'm actually going to start at -6 so you can see where I'm starting from as far as similar to the last one and go to +4 here. So -6, -5, -4, -3, -2, -1, 0, 1, 2, 3, and 4. And again, not all of these points fit, but this is what I'm copying down so we can see that movement, that change. So it starts at -6, 64, -5, 32, -4, 16, -8, or excuse me, -3, 8, -2, 4, -1, 2, 0, 1 is the same. So that y-intercept is the same. And then we're taking half of 1. Well, that's 0.5 or 1/2. Then we're taking half of 1/2. Well, that's 0.25 or 1/4. Then we're taking half of that. Well, that's 0.125. That's 1/8. Then we're taking half of that. Well, that's 0.0625, 0.0625, excuse me. And that's 1/16. And so you can see that we're continuing to take half and half and half and approaching the asymptote, which is the same. That asymptote is the same. And if we think about it, it's the same number that's being added or subtracted at the end of my equation. There's nothing being added or subtracted at the end of my equation. There's nothing being added or subtracted at the end of my equation. So what's my asymptote? 0, since 0 is being added to the back of my equation. Y equals 0 is my asymptote, and I can tell that looking at the equation. So let's get these points on here. Oops, I didn't mean to press anything, my bad. Okay, let's get these points on here. -4, 16 seems as the closest you can get. -3, 8, -2, 4, -1, 2, 0, 1. Then remember half, right? So halfway between 1 and 0, halfway between 1/2 and 0, halfway between 1/4 and 0. I'm really not going to be able to show 1/16. So again, arrow is straight, connect. We're heading towards that asymptote, but we're not getting there. Arrow, stop at that point. Don't try to extend. And then label y equals 1/2 raised to the x power. This time, this is a decay, an exponential decay function, because as x is getting bigger, y is getting smaller. And we know with all of our exponential functions, we label that asymptote on here. So I'm getting it right now. As we already said, it's y equals 0. This is that equation we cannot touch or cross, y equals 0. So we've looked at an exponential growth function. We've looked at an exponential decay function. Let's just compare. Each function has a y-intercept of 1 and an asymptote of y equals 0. Must state y equals 0 because it's a horizontal line. It's straight across. Okay, so just like how the axis of symmetry in a parabola is always vertical, so it's always x equals, your asymptotes for our exponentials will always be straight across, so they're always going to be y equals. Okay? What can we conclude from the bases? If your base is greater than 1, then the function increases. That's the growth function. If your base is between 0 and 1, the fraction like this one, then the function decreases. Okay? And it's always reading left to right like we do in English, right? So that's the reason we call this growth and this decay. That's the reason we call them those. All right. Pause it here if you need to make sure you're getting those pieces on your graph and get the points labeled and connect correctly and put your arrows correct and get your labels correct and understand why I'm calling this increase or growth and why I'm calling this decrease or decay. So pause it here if you need those values. If not, let's go. So what we're going to do is we are going to compare this graph right here to two other graphs that I'm about to do with you. Okay, so we're going to compare those two graphs real quick. And what I'm going to do is move fairly quickly and do different colors while I'm doing this so that you can see these differences. Okay, so I'm going to clear this out and put 2 to the x power. Then I'm going to arrow down, and in red, I'm going to do 5 times 2 raised to the x power. And then I'm going to arrow down further, and actually I'm going to do orange, right? So I'm just going by color, so I don't have to change the color, right? So now I'm going to do -3 on the outside, and then in parentheses 2, this is my base, raised to the x. So make sure you have those in correctly. Okay, make sure you have those in correctly. And again, I just chose to move down because I wanted a bright color when I graph. So now I press graph to see my original blue, now my red, what movement happened, now my orange, what movement happened. Let's think. Did my asymptote change with any of these? No. This one, the y-intercept changed, and so it's a more rapid increase. The orange one, the -3 in front, that one flipped the other way, but still has an asymptote of y equals 0, meaning it can't touch or cross the x-axis, right? So this is actually those comparisons there. That front number is changing the y-intercept, or if it's negative, the direction I'm going. Okay, you see that? That's where those pieces are coming from. So you can also see second and graph are my tables of those points, and just look straight across at 0. Okay, before I put these things on the graph, just look straight across at 0 as an x value. We go from 1 to 5 or -3. What was the number in front of the base? 5, -3. See that? That number in front of the base can determine where your y-intercept is, as long as your x stays just an x as your variable, okay, and your exponent. All right, notice none of these have another number being added or subtracted at the end, which is again why their asymptote is y equals 0, okay? All right, so I'm just going to copy a couple of these onto here. And again, these are already filled in. That was my blue that I'd already done. Let's get some red and some orange on here. So -4.3125. -3 is 0.625. -2 is 1.25. -1 is 2.5. 0, 5. Oh, I'm still doubling, right? 2.5 plus 2.5 is 5. And then 5 plus 5 is 10. And then 10 plus 10 is 20. And then 20 plus 20 is 40. Whoa, look how quick that happened. And then 40 plus 40 is 80. Very rapid increase there. Okay, now if I think about the other way, so in the other direction from this, -4, -0.188, -3, -0.375, -0.75. Oh, wait a minute. -1, -1.5. If I add -1.5 to -1.5, I get -3, 0, -3. If I add -3 to -3, I get -6. So it's still doubling again because the base is 2 for both of these. They're still doubling, just one so much more rapidly because it's got that 5 out front that we then multiply by. And the other, in the other direction, going negative infinity, because it's got that -3 out front. So see how this is still the same pattern? It's just dependent on that number in front of the base where we're going with it. Okay, the asymptote, and I'm going to leave that as blue just because I want you to know that that asymptote still compares to that original graph as y equals 0. Oops, sorry. I was treating this graph like the y or the x-axis was at the bottom still, and that's not the case. So this asymptote is still y equals 0. Okay? Oh, you didn't see me make that mistake, but you'll see it now. There it is. See? Accidentally tried to put that asymptote too far down. 0, 5, 1, 10, 2, 20, already off the map. Now back this way, -1, 2.5, well, that's about here. And then -2, 1.25, so here's 1, 1.25. So let's see, 0.625, well, it's below 1, right around like here. And then 0.3125, well, that's kind of like here. And that is definitely close enough to the asymptote that let's just connect. And again, very rapid increase. And label. Asymptote already labeled, and I kept it in blue because of this graph being in blue on the front. Now this guy, 0, -3. Notice how I'm always doing the integer points first and then 1, -6, and that's all I can fit because this is just a 6 by 6 grid. So now let's head backwards. -1, -1.25. -2, -0.75. Sorry, my asymptote's kind of in the way, my labeling of my asymptote. -3.5, and that is definitely enough, right, to show my approach to my asymptote. Definitely enough. My writing of my asymptote is in the way. I should have waited. There we go. Okay. And again, let's think about each of these. Let's think about each of these, right? This was the blue one. If I plug 0 in for x, which is the y-intercept, has an x value of 0. If I replace that, anything to the 0 power is 1. So guess what that point is? 0, 1. Look up. There it is. 0, 1. Now let's do it here with the red one. So y equals 5 times 2 to the 0 power. Well, anything to the 0 power is 1, but don't forget, now you've got this 5 out here. So the 2 to the 0 power becomes the 1. 5 times 1 is 5. Guess what this one is? 0, 5. And oh, look, 0, 5. Last but certainly not least, and then you'll understand, this is why I'm plugging that value in as 0, right? 2 to the 0 is 1, but I've still got to multiply by -3. And -3 times 1 is still -3. So this is 0, -3. And that's, again, this value right here. So we can see it right here. We can see it right here. Okay, those are the correct y-intercepts. So what made these change? The a value, the value in front of the base. And remember, the base is always that number being raised to the power. Okay? All right, I know exponential stuff can be tough, but use that graphing calculator to help you as you're going. Okay? Ask me for help. We can always interpret these. We can always work together on graphing those fractional points and thinking on how I think about those. So I can always look a little bit further into how I do those. Okay? But we want to know basic shapes. We want to know how to recognize the asymptote. We want to know what the y-intercept is. Okay? The y-intercept, remember, always has an x value of 0. Guys, have fun graphing your exponential functions. Rapid increases, rapid decreases towards an asymptote, but never touching or crossing it. Every exponential graph has an asymptote, a horizontal asymptote that must also be labeled. Okay, good luck. I will be seeing you guys very soon. Bye.